This is the last session of the whole class. And what I want to cover is just kind of a really quick review of what we have covered so far. And also I want to share you some like really good views. I mean, it's more like how do you try in the literature of machine learning? So what are those communities and what are their focus? And the reason why I'm doing so, I'm going to explain when we are in the latter slides. And in the end, I'm going to recommend 4 books. So they're not relevant to machine learning, but I think they're really, really great books. So again, to recap, I mean, the objective of this class is to help you to be able to build the tools and for a few simple machine learning methods from scratch. And then hopefully you can read those complex machine learning methods at the source code level. So I hope we have not failed. Hopefully we reached our goals. I mean, especially this two key results we're aiming for from the beginning of the semester. So just again to recap, this is almost the most important to think about what differs machine learning versus the traditional programming. So the traditional programming is you have data and you have algorithm, you have a programmer to give you the code, right? But machine learning kind of different here. So you provide with data and output, and then our machine learning method give you this model or the algorithm. And so essentially you can tell in this two different kind of protocols, and the data really plays much bigger roles in the machine learning kinds. And also that's one of the reasons why machine learning becomes more and more popular and more important. It's because, I mean, everything is moving to the digital, right? Means now it's really essentially we are having this digital form more than the physical form. So every one of us using cell phones, cables, whatever, and all those different kinds. And this is just consumer side, but not to mention all this, all these big institutions, big aspects of the whole human society and the whole planet Earth. I mean, honestly, everything going to digital, we just recording so much data. And then the best way to make use of this data, I mean, just there's no way to rely on the manpower or our human brains. I mean, there must be a machine that just runs constantly to analyze those data, organize those data, and then use those data to make decisions. So in the end, I mean, there's this machine learning got more and more important. It's really background conditioned on this digital over physical revolution. I mean, before the AI. So there are 2 modes, and I hope you still remember. So there's a training mode and deploy mode. And then we always organize everything in our nutshell view. So there are 6 elements in our nutshells, and then data, task, representation, score, search, and model. So, and we roughly sectioning our class into 6 sections. So there's this first section is basic supervised regression on the tabular data. And then is the basic deep learning on the 2D imaging data. Then this deep learning and generative model on the 1D sequential data. And then we talk about supervised learning, more advanced, tree-based, and on the tabular data. And then the last week was on unsupervised data. So I try to have reinforcement learning, but so because of the schedules, we kind of skip it. Hopefully you have time to touch that later. And then today is the wrap up. So beyond the wrap up, we also have other like invited talks like AWS, this invited speaker, and also about secure machine learning. Yeah, sorry about my background. So there's some kind of truck going on. So, and plus our TAs, both TA made really great Resetto like slides. So again, with regard to data, we covered tabular, imaging, and text, and then with regard to tasks, we talk about regression, theorem, classification, unsupervised models. So mostly we covered classification data. So inside classification, we have 3 types. I mean, this discriminative type, generative type, and instant-based types. And then we use like almost 2 sessions to cover what is the most state-of-the-art deep learning. So the deep learning, again, we organize the whole thing through our nutshell views, but we are adding one more variables we actually did not touch in other section is the hardware variable. So in fact, I mean, there's so many advances, so many breakthroughs, interesting work adapting this data-generated program, machine learning models on the hardware. So I really feel this vertical integration type of direction, it's very, very promising. And then this page essentially, in fact, is the most important page I want to hopefully remember. And this is more like a machine learning good practice or good habit. So it's guided by the learning theorems, but it's really about how you use how you use data, how you build a model, and this is more about the workflow. And the workflow we always emphasize is k-fold cross-validation, and then the grounded on this basic decomposition, something called expected prediction error, and then we talk about bias variance trade-off. And when you understand the bias variance trade-off, you understand overfitting and underfitting. So this is two different kinds of bad generalization, right? So the whole goal of machine learning is to have good generalization. Then what are the bad ones? So there's one kind is overfitting, the other kind is underfitting. So when you handle your data, training on your model, you really need to figure out if it doesn't work well. Is it overfitting problem or is it underfitting problem? Because that's two different ways to do the remedies. So besides, we have a little bit quick discussion about generative versus discriminated classifier, but that's pretty short. And then very, very important is I want you to hopefully you remember this. I mean, when you trying to use data and on the model, you really need to kind of more like detector. You need to figure out, am I in the overfitting paradigm or in the underfitting paradigm? Now, what are the mechanism actually this control the overfitting, underfitting? So we actually talked about two. So one kind is you adjust the model complexity or model capacities. So, and then the other kind, you use training size to control the overfitting, underfitting. And very, very importantly, in the homework, we asked you to try to get familiar with 3 different plots. So the first plot is the training validation loss versus epochs. This is really to help you to understand or to look at your optimization. So this is more about optimization. The second curve is training validation loss versus hyperparameter. And this is really about this, something people normally call this, I think this is called like tuning curve, or yeah, tuning plot. And the last one is this varying the training size. This is called, and this page is the most important page. I want you to totally get it. I mean, after this class, if you don't understand this, it's a little bit failing on our side, I have to say. I mean, remember this page and try to understand it very deeply, because this is about good practice, and it's about truly how you are going to be a very good machine learning practitioner. All right. Okay. So in the beginning of the class, we have a fully blank, empty table, and now we totally filled every entry of here. So feel free to look over each one of this if you want to review me in the future. So we really covered a lot. We have really, really covered a lot. So because of the shortening of the class, I mean, I know this is a little bit too much, a little bit overwhelming. So how to say this? I mean, I feel very honored, you know, to can be able to share you at this difficult time. I mean, that's why I always try to teach you a little bit, whatever I think is important. I want to deliver those. I mean, hopefully that's not too overwhelming. All right. Okay, so now this is the philosophy page I really want to show you. So in the beginning of the class, I showed this page in the first class. I'm not sure if you ever get it, but this is really the most important page, how to kind of guide me. Again, so this is about taxonomy of cognitive learning. when we learn anything, we normally start, the lowest level is remember it, and then reach the level of understanding, and then reach the level of applying, and then reach a level of evaluate, and then you do creating. So hopefully now you understand. I mean, we actually already finished the remember. We finished the remember level. We are finishing the understanding level. We also did a lot of applying level. And also my nutshell view is really exactly in the analyze level. So, and the next one is actually the evaluation level I want to show. I'm covering all of the three, the under 4 levels to prepare you to be able to innovate, which I think is the most important, at really the highest level in terms of technology and engineering. And now you are very, very good in the analyzing level already, and some of you are already in the evaluation level. Okay, so to be able to evaluate and innovate, I mean, let's actually see the next page about how to do evaluation. So this is from scikit-learn, and actually scikit-learn has this, I think I already shared you the link. They're just having this kind of simulation data or whatever data, they compare all different classifier. In this case, the first row is nearest neighbor. So this is nearest neighbor, and this is SVM, this is RBS FSVM, this is Gaussian process, this decision tree, random forest, and all so on and so forth. Actually, when you look at this kind of graph, you start to realize the differences among across different methods. I mean, when you later, hopefully you can do innovation, and also hopefully you really understand deeply, can be careful in picking up whatever method is to understand. I mean, different method have different assumption on data. They have different scalability profiles at training, different latencies at testing, different model size, different level of interpretability and robustness. Just visually, when you compare them, you can actually tell how different these different algorithms are. And then there's another figure we shared, I mean, actually from scikit-learn. Again, try to play with it if you have time. It's comparing unsupervised method. So these are different columns, are different unsupervised approach. I mean, and different rows are different kinds of data. And here there are actually 5 different data. And you can actually tell on this 2 circle data, this is called a mini batch k-means. I mean, really just separate into 2. And then, but this something called, it's actually hierarchical clustering, can totally get it. So get the 2 rings, right? But the k-means just cannot. I mean, in the end, it's really not about who is much better than the other. It's really about my data. My data, maybe this method fits more because my data matches the assumption of that model, that method more. So which you just, it needs you to have good understanding of the method and also good understanding of the data. So like I emphasized last time, because this scikit-learn, I mean, PyTorch, all those different fantastic library, the machine learning becomes more like a commodity, right? It's just everywhere. It's really easy to use. I mean, high school kids or maybe even middle school kids can use it now. And they style transfer, they do this imaging face transfer. It's really a few clicks. I mean, what differentiates you from the normal users? And it relies a lot on your data taste, of course, and also that page I showed you, good practice of machine learning workflow, and good understanding of the data, the method assumption. So good taste on data, good understanding of model assumption, and good habits on workflows. And remember that three factors. I mean, help you can in the future. This can help you. All right, so this is about evaluation. Okay, so now like I want to do more evaluation. So it's more so analysis. So let's see how do this the field machine learning research field, can decompose, why they're doing so. So roughly, this book is called the Master Algorithm, and it categorized the tribes. You can think about researchers in the literature work on machine learning can be grouped into 5 groups. So the first kind is called Symbolist. They're really using a lot of logic type-based method. The second kind called Connectionist, and this is the group actually who are the major force to push the deep learning, and their fundamental focus is to emulate the brain, how brain works. And the third is called Evolutionist, and the fourth is Bayesian, and then last and Analogizer. So let's just go look each one of them. So Symbolist, their fundamental, there's a lot of philosophy origins, right? So they start from logic, and their key method is like inverse detection. And Connectionist, there has a lot of origin from neuroscience, and their key method is back propagation. Evolutionist, and they have a lot of ideas from evolution biology, and their key algorithm are genetic programming. And the Bayesian, and it's this most origin from like statistics, and their key method is probabilistic inference. And this analogizer group, they got a lot of idea actually from psychology, and the key algorithm is the kernel and this collaborative filtering, this matrix decomposition based method. So Symbolist, it's this is a typical, most, you can think of the 3 godfather, and like from Tom Mitchell, Ross Quinlan. I hope you got a little bit. So Tom Mitchell is almost the author of the first book on machine learning. Ross Quinlan is the author who truly make the decision tree to be almost the first successful decision tree method. So the fundamental idea, it's more like a rule-based. You can just think, it's logic, and then logic extension is rule-based. And the second group is Connectionist, and it's Yann LeCun, Jeff Hinton, Yasha Banjo, and they are the recent Turing Award winner, and they're the main driving force who actually got this deep learning like industrial revolution going on. So we already talked a lot about this, so we will not talk too much, but in the end, they got a lot of insights from neuroscience. And then the next is called Evolutionaries, and they are, so this seems to be, we don't even touch anything about evolution method, right? But in fact, before this numerical type of machine learning got really dominating, before that, it's the evolution method, genetic programming, is the dominating method to, it's really the dominating method before the more numerical type of machine learning models. It's just, how do you learn trees, right? How do you learn this kind of logic or rule-based symbolic models from data? The genetic method, it's clearly it's a very almost the dominating approach by then, actually then. So hopefully you know what is genetic method. I will not cover that. I think our algorithm class covered this. So it really, you think about, it's more like, it just got a lot of idea from how biological species evolve from generation to generation. All right, so the fourth one is called Bayesian. Bayesian, there's this crowd is this really mostly from statistics, and their main mechanism is probabilistic inference, and Judea Pearl and Michael Jordan, maybe you already heard about, and they are also really important person make machine learning like now. So the fundamental like secret sauce in this crowd is this probabilistic formulation, probabilistic inference, which you learned a little bit in your Bayes model. And the key focus of this group is about modeled uncertainty. So this group dominating the machine learning. So that was actually when the genetic algorithm or genetic crowd dominating is actually the machine learning it doesn't model uncertainties at all. It's not stochastic. There's not much randomness. It's really just I give you whatever samples, I go down past the rules or the logics, and I make a decision. So it doesn't capture uncertainty. And then the Bayesian crowd, I'm bringing in the probabilistic inference tools to make the machine learning to be able to model and to be able to consider the uncertainties and also to model the uncertainties. All right, so that's the fourth, and the last group is called Analogizer. You can actually already tell what does that even mean, right? So it really comes from this fundamental philosophy. It's analogy. So what is similar to the other? So that's the most important philosophy this group relies upon. So this actually it's very, very, very influential. We don't talk about this much, but you can think about K-nearest neighbor. Yeah, K-nearest neighbor is the most classic recommender, this kind of analogizer, right? So I'm making decisions according to whoever is similar to me. That's the most fundamental philosophy or intuition behind this kind. So there are many different approaches in this analogizer crowd. So for example, so you try to recommend a user movie or a product or a hotel or a restaurant. It's all the same. You just try to figure out who is a similar user to this current user. And if these two users read both some kind of articles, I mean, you think they're similar, and then you're going to recommend the left users this new reads and to the right user. That's all it really relies on. It's analogy, right? But how to implement the analogy, there are many different kinds of methods. So classic is you just directly use distance measure, or you can use matrix factorization, and SVM is another kind. Actually, it's a very principled way to model such intuitions, this kind of analogy type of intuitions. All right, so this is like a big picture summary, and this you can actually tell. I mean, the whole tribe and the whole literature of machine learning, they're not focusing on the same thing. In fact, the symbolists they actually focus more on knowledge representation or knowledge composition. And the connectionists, they focus more on representation and also numerical optimization. So this is some issue called credit assignment. So maybe this is too Asian term for you, but so in the end, you try to figure out, I mean, how to figure out the right signals based on the last error signals. You try to go back and to figure out the right assignment, right weights. Yeah, so, and then this is the connectionist focus, evolution tribe. The focus is about the discrete combinatorial search. So this is a search. This is an optimizer. And Bayesian is about uncertainty. This is about distribution. And like analogizer, in the end, what they focus on is on similarity. So if you think about what do similarity even mean, so in the end, similarity, it's more about this kind of reconstruction laws, right? Who is who and similar, and you try to match them, this kind of matching laws. Evolution focus on discrete optimization, connectionist focus on representation and numerical optimization, and symbolist is more a rule-based representation. All right, so I hope this gives you a good analysis of the literature. I mean, to whoever wants to maybe a graduate studies, I think this can give you some sense about different schools and different groups. All right, so this is the last 4 pages, and I really want to share you. So the first is this book I already shared, and then this next book is something called Algorithms to Live By, the Computer Science of Human Decisions. So this book is fantastic. It's a fantastic exploration to show you how computer algorithms applied on everyday life, and I highly recommend you to read it. And the second book is this book called So Good They Can't Ignore You. So I really want you to think about, I think maybe some of you already know about it, is this 10,000 hours of deliberate practice rule. So how to become expert. You really need to have that 10,000 hours of deliberate practice. And if without it, I mean, don't even think about yourself as an expert. All right, so there you really have a long way to go. So I think hopefully this class give you a good foundation, but keep in mind you need to like have more deliberate practice, deliberate learning. So the third book is, I really want to share this book. It's called Ego is the Enemy. Ego, like, it's really the worst thing actually hurt you and then block your growth, also blocking your productivity. And then its ego will turn this minor or accomplishment or whatever into the major events in your head, actually in your head. I mean, it's not real. I mean, it stay very humble. It's all the way very humble. And keep in mind is work. The most important thing you can do to fight your ego is to focus on creating values, sit down and put in hours, invest in yourself by thinking long term. And this is the word I want to pass to my children. I mean, hopefully they listen. I really want to share to you too. So, okay. So the last book is Homo Deus, and it's really from Yuval. I kind of look up to this author, and I think I shared this book in the beginning is, so, this technology, AI, and also biology, there's so many things like changing our society so fast. We always think they are there, but they're just quickly changing. And they're changing by the technology, they're changing by this so big differences, so big changes of the world. You really have to remember, you have to keep inventing yourself. In this kind of era of uncertainty, keep inventing yourself is the only way to deal with it. And also, plus, forget about the ego work and then focus on creating values. And I think this summarizes everything of the class.